Bismillahirrahmanirrahim. Assalamu alaikum students. Today our topic is, remember last time we discussed the first law of thermodynamics. Now our topic is work and the PV diagram. PV diagram for a gas. This is our topic. Work and the PV diagram for a gas. So first thing first, we define an ideal gas, and for an ideal gas we have an equation PV is equal to nRT. What is P? P is pressure in the gas, V is volume occupied by the gas, N is number of moles in the gas, R is universal gas constant, and T is absolute temperature. That means temperature in kelvins. The absolute temperature. So N is expressing the amount of the gas in terms of number of moles, V is volume, P is pressure, T is absolute temperature. So all gases, all real gases must be knowing this. Obey this equation. That means they come close to being ideal if they are kept at low densities, or we say if they are kept at high temperatures and low pressures. So this is a model gas. We understand the behavior of gases through this equation, right? So this equation says if we have a gas and its pressure, for example, is kept fixed, if you make changes in volume, temperature will change in order to keep PV is equal to nRT. Because these two things, N and R, are constant. If you take certain gas, now with certain amount, number of moles will get fixed, R is constant. So you have three variables to play with. If you make change in one of these three PVT, among other two, one or both will change, but this identity will hold. Always PV will be equal to nRT. If you make change in T, V may change, P may change, both may change, but PV will stay equal to nRT. Same holds true for VP, right? This was first thing. Now, I take a gas, keeping in view this equation, I take a gas. I will draw the figure, then I will explain it to you. Right? So let me complete the figure. I will explain. This is my adiabatic wall. Then this is gas inside it. This is piston of area A. Right. Okay. So I have a gas inside this container. It's a container and there is piston fitted with it, which is movable. This piston is also frictionless. So I have a container containing a gas. It has piston and that piston is movable with area of cross section A. Now this red one line is indicating its initial position and then this dotted blue line is indicated that piston has moved through certain distance dx and this container is adiabatically shielded outside, right? That means no heat exchange can take place between the system, my gas and surroundings because adiabatic wall is enclosing the gas. Now idea is like this. If I move this piston, I can expand the gas, I can compress the gas. If I move this piston to the right, gas will expand, its volume will increase. If I move this piston to the left, because it is movable, gas will be compressed, volume of the gas will decrease, right? So in both cases, I can change the volume of the gas. Now, if when, as I said, this is gas, its behavior is controlled or governed by this equation, PV is equal to nRT. So if I move the piston to the right or to the left, I am changing the volume of the gas. Then what will happen? Either P or T or both will change in order to keep PV is equal to nRT, right? Now question is how to move this piston. This piston can be moved suddenly. For example, if I move this piston suddenly to the left, what will happen? Gas will unsettle. It will not remain in its equilibrium state. Remember the equilibrium state we have already discussed. If I move this piston suddenly to the left, the region of the gas which is closer to the piston will have higher pressure and the region of the gas which is far from the piston will have lower pressure. So gas is unsettled, you cannot assign pressure to it because we know we can assign the values of pressure, volume, temperature to a gas only when it is in thermal equilibrium with itself, when it is settled, when its macroscopic variables are constant in time. They are not changing with time, right? So we cannot move this piston suddenly because we cannot assign our variables to the gas. Gas will never be in its equilibrium state. Then what we do, we move this piston infinitely slowly, very slowly in small steps. We move it, we first wait for the gas to settle down, then we assign the values of pressure, volume, temperature, and specify its macroscopic state. Then we move it further towards left or right, slowly in small steps, and allow the gas to settle down and assign the values of PV and T to the gas. So this way, if we move this piston infinitely slowly in small steps and we and wait after every movement for the gas to get settled, we can assign macroscopic variables to the gas and thereby by moving the piston, we are moving this gas through a series of macroscopic states. Each macroscopic state is specified by the set of values of PV and T. Now, such a process in which we move this piston infinitely slowly in small steps is called quasi-static process, right? This process is called quasi-static process. We can have quasi-static expansion, quasi-static expansion, or we can have quasi-static compression, right? So if I move this piston to the right, I'm expanding the gas. That is, if I'm doing it quasi-statically, then the process will be quasi-static expansion. If piston is moved to the left, right, then I'm compressing the gas. If the process is done quasi-statically, I'm doing quasi-static compression of the gas. So we define this quasi-static process. We say in a quasi-static expansion, same is true for compression. In a quasi-static expansion, the piston moves infinitely slowly with no acceleration, so that the gas moves through a series of equilibrium states, right? By quasi-static expansion, piston moves infinitely slow with no acceleration, so that the gas moves through a series of equilibrium states. Three things are important. One, piston moves infinitely slowly, piston has no acceleration, and gas moves through series of equilibrium states. Each equilibrium state will be specified by the values of macroscopic variables, pressure, volume, and temperature, right? And remember, when we say piston moves with no acceleration, from Newton's second law, if something, Newton's second law says net force is equal to mass into acceleration. If the acceleration of a body is zero, the net force on the body must be zero. So remember this in your mind, that when we say piston is moving with no acceleration, then means net force on it must be zero, right? So let us move. Now, when we have to represent the macroscopic state of a gas, we represent it on PV diagram. That means we plot pressure on y-axis and volume occupied by the gas on x-axis. This diagram is called PV diagram. For example, if I take some point on this PV diagram, that point has value of pressure, for example, P naught, and some volume value. If I take this point, here pressure is this V0 and volume is this value here, V0. So each point in this diagram is representing a macroscopic state of the gas, right? So each point on a PV diagram represents a macroscopic state of the gas. So when I say, or when I said that if we move this piston to the right, we expand, allow the gas to expand. So in PV diagram, what will happen? We are moving the gas through different states. So point will move, right? Keep that in mind. Now, let us take a gas. It will have some pressure, some volume, and we allow it to expand against the piston. So what will happen? For example, this is my volume, this pressure. Now, let initially gas be in this state. Here pressure is some value and volume is V1, right? Then I move this gas to this point. Pressure is P and volume is V2. This means I am moving this gas from this state to this state. It means that during the gas is expanding because volume is increasing, but pressure is staying constant. Remember, this height is staying constant. So it is simply what? It is expansion. This diagram is representing expansion of the gas at constant pressure, right? Now what happens in this expansion? Pressure is staying constant, but volume is changing from V1 to V2. Now, this gas is doing work on the piston or its surroundings. When piston moves to the right, gas expands. Let the piston move through distance dx. The piston moves through distance dx and A is the area of the piston, then the volume of the gas will change by amount AdX, right? What is AdX? AdX is dV, change in the volume of the gas, right? Now see, we said pressure is constant. And when piston moves to the right, we said piston, we are doing it quasi-statically. Piston has zero acceleration or no acceleration. That means net force on it must be zero. That means gas is doing work on the piston against the external agent, that is surroundings. On piston there must be no force. So outside atmosphere and inside gas, the forces exerted by these two agencies must cancel out. The gas is doing work on the piston against the surroundings, and that work will be force times the distance moved by the piston. So if dW is the amount of work done by the gas on the piston or surroundings, that is one and the same thing. This work will be force times the distance through which piston moves. Now, force exerted by the gas on the piston will be pressure times area, because pressure is by definition force per unit area. So if P is pressure in the gas, F is force exerted by the gas on the piston, A is area of the piston, pressure is force per unit area, so force exerted by the gas on the piston will be pressure times area. Now we said AdX is change in the volume, so it is PdV. So if the gas expands and its volume changes by amount dV, if P is the pressure in the gas, the work done by the gas on the piston or on the surroundings is given by PdV, right? So work done by the gas on the piston or surroundings when piston moves through distance, infinite small distance dx, and the volume change of the gas changes by infinite small amount dV is pressure times dV. Now this pressure times dV in the diagram we can find C. This is dV and this height is P. So this dW, I'm actually showing it for large change in volume, but it is actually for small change in volume, right? So remember this figure is an exaggeration. Actually volume has changed by infinite small value. Now here it will not matter because pressure is staying constant. We can take large change in volume also. The idea is this work is actually this area under this curve. So remember, when gas moves from one state to another state, in the PV diagram there will be some curve defining this process, and the area under that curve will represent the work done by the gas, right? So area under PV curve represents the work done by the gas T, right? Now this is true when pressure stays constant during this infinite small volume change. Then if we have to find the work done by the gas for a large change in volume, we have to integrate this to get the total work. But during that integration, we must know how pressure changes during the process with volume. We must have that function, only then we can integrate. But for infinite small change in volume, you can write P times dV because pressure during infinite small change in volume stays constant, right? Now this equation can be used for compression as well. If there is compression, then final volume is less than initial volume. dV will be negative and the work done by the gas will be negative. So for expansion, work done by the gas is positive because dV is positive, final volume is greater than initial volume. And for compression, dW is negative as dV is negative because final volume is less than the initial volume, right? Another thing, I will draw a diagram, then we will explain it. So idea is like this. I want to check whether work done by the gas is state function or not. So this is my PV diagram. So I take the gas from state 1 to state 2 through different paths. So V1 V1 represents the first state, V2 V2 represents the second state, final state. Let it be P1 V1, let this be P2 V2, P1 V1 and P2 V2. So what I do, I take this gas from state 1 to state 2 through 3 different paths. Let this be my path A. Let this be my path B. Let this be my path C. Now understand this. I'm saying I have a gas. It is initially in state P1 V1. I want to take it to state P2 V2. Right? Now I do it in 3 different ways. That means I'm using 3 paths. In first path A, I expand the gas from P1 V1 to P1 V2 up to this point. Pressure is staying constant and volume is increasing from V1 to V2. That means I keep the pressure of the gas fixed but expand it from volume V1 to V2. Then from this point to this one, what I do, I keep the volume V2 fixed, decrease the pressure of the gas until pressure becomes P2. That means during path A, the work done by the gas is this area. This area represents the work done by the gas. So this is my work done by the gas, right? And that work is done by the gas in this piece of the path. In this piece of the path, there is no change in the volume of the gas. And if there is no change in the volume, there is no work done. So the work done by the gas in path A is done in first piece, right? Come to set path B. Here what I do, first I keep the volume of the gas fixed V1 and decrease its pressure until pressure becomes P2. So in this portion, there is no work done by the gas because volume stays constant. Then I expand the gas at pressure P2 until volume becomes V2. So the work done by the gas in path B is this area. This is work done by the gas. And that work is done by the gas in second piece of the path, not in first piece, because in first piece there is no change in the volume. Now, in case of path C, I am changing the pressure and volume simultaneously. So the work done by the gas is this area under the curve. So this is my work done by the gas. What is the conclusion? I have a gas. In all the 3 paths, initial and final states are same. P1, V1, P2, V2. Work done in 3 paths is different. Here I have a larger work, different than this, and this work is different than this. So idea is, therefore the conclusion is work done by the gas depends on the path taken. That in turn means that work done by the gas on the surroundings depends on the manner in which work is being done, right? That in itself means that work is not a state function. If it was a state function, then work should have been same because initial and final states are same. But even if initial and final states are same, but work is changing with the path taken. So work done by the gas, conclusion is work done by the gas is not a state function. You need to remember this. We now focus on another thing. Let this be my PV diagram, and let some gas be initially in state P1 V1. I take it to state P2 V2, right? So what I do is I take this gas from state 1 to state 2 along path A. Then I take it back from state 2 to state 1 along path B. Right? Understand this. Gas is initially in state P1 V1. I take it to state P2 V2 along path A. Then I take this gas back from state P2 V2 to P1 V1. So what is happening? In path A, I'm expanding the gas because volume is increasing, right? And the work done during that expansion in path A is this whole area. Try to understand this. Is this whole area, right? Then what I do, I take this gas back from state 2 to state 1. I'm decreasing the volume. Here volume is greater, here volume is less. That means gas is compressing. Or I can say gas is doing negative work. Remember, work done by the gas is PdV. In path A, dV is positive, work done by the gas is positive. In path B, dV is negative, volume is decreasing, work done by the gas is negative, right? And that negative work is which area? That is this area, lower area, this area under curve B, path B. So what is net work done by the gas? Net work done by the gas is positive because this area is bigger and lower area is smaller. So net work done by the gas is positive, and that positive work is denoted by the area enclosed in this loop. So this is my network. Net work done by the gas. Right? What is the conclusion? Conclusion is if a gas moves in a closed loop in PV diagram in clockwise sense, this clockwise sense, the way clock moves. then what happens? Net work done by the gas is positive, and that network is represented by the area enclosed within the loop. What about this situation? If I have PV diagram this way, initial state is P1, V1, final state is P2, V2. I take gas first from this state to this state, then back. What is difference between this and this? Difference is here I am first expanding the gas. Path A is this, path B is this, right? I'm expanding the gas first, then compressing it. The first work done by the gas is work done by the gas during path A is this area, then work done by the gas in path B, gas is being compressed, is negative. And that is this whole area, right? Here, net work done by the gas is negative. The negative work is large. This area is bigger. So here work done, net work done by the gas is negative, and that negative work is represented by the area enclosed in the loop. Here net work done by the gas is positive. Here net work, this area represents net work done by the gas, and it is negative, right? What is the conclusion? Conclusion is, if a gas moves in the PV diagram in a closed path in clockwise sense, net work done by the gas is positive, and that is represented by the area enclosed. If it moves in anti-clockwise sense, net work done by the gas is negative, and that is represented by the area enclosed. Now another thing. At the start, gas was here, now gas comes back, right? This also indicates that work done by the gas is not state function, because even if gas has retained its state, the value of net work done by the gas has not retained its value, because initially there was no work done by the gas. When it comes back, situation is different. State has been retained, but value of work done by the gas has not retained. First it was 0, now it has some positive value. So work is not a state function, because state function means if a system comes back to its original state, the value of that function must become same, must retain, must return to its the initial value, like internal energy. Internal energy, last time we defined, it's a state function. So if a system, internal energy here is different than internal energy here, but when gas comes back, it has same internal energy, but it has not, the value of work is not same. And same situation here, work is not same. The work is not a state function. And let us apply Newton and this, not Newton's, let us apply first law of thermodynamics to this. Gas. First law says net heat put in the system is equal to work done by the system on the surroundings plus change in internal energy. Now in both these cases, change in change in internal energy is zero. In any closed path, change in internal energy is zero because it is a state function. Now, we said here, I name this for clockwise path. For clockwise path, delta U is zero, Q is equal to W. For anti-clockwise path, again the delta U is zero, Q is equal to minus W because work done by the gas is negative. What's the meaning of that? Meaning of that is for this path, this enclosed area is work done by net work done by the gas, and that is equal to heat put into the system. This gas has absorbed that much heat from the surroundings, which is the work, net work done by the gas. This Q is equal to W. And in second situation, in this anti-clockwise path, net work done by the gas is negative, which is enclosed area. That is also equal heat released by the gas, because Q negative means heat has been released by the gas, right? I summarize it. If a gas moves in clockwise path, in the clockwise round path in the PV diagram, net work done by the gas is positive, that is area enclosed within the loop, and same is the amount of heat absorbed by the gas. Here, same is the amount of the heat released by the gas. Now again, heat is not a state function. Heat is also not a state function, because even if the system has come back to its initial state, the value of heat is not same. Here it has absorbed heat, here it has released it. So heat is not a state function. Heat is not a state function. So first law, net heat put in the system is equal to work done by the system plus change in internal energy. This is it relates three quantities: heat, work, and internal energy. Right? Heat is not a state function. Not a state function. W is work is not a state function. Not a state function. Internal energy is a state function. So you have to remember it in first law of thermodynamics. Two quantities are not state function, heat and work. One quantity, internal energy, is a state function, right? So when we say some system, when its temperature is high, it is hot. If we say it contains a lot of heat, that is incorrect. Or if we say it contains a lot of work, that is also incorrect. It may contain a combination of both. So better is to say it contains a lot of internal energy, because it is a state function. It specifies the state, right? I repeat, if I have some system and it is hot, if I say it contains a lot of heat, it may contain work also, because you can increase the temperature of a system by doing work or heat or a combination of both. Now, neither heat nor work is a state function, so it is incorrect to say if a system is hot, it contains a lot of heat, or it contains a lot of work, or it contains a combination of two. It's better to say it contains a lot of internal energy, because that is a state function that is specified by the state. So it completes our discussion today. I will give you homework. So this is your homework. Question is like this. It's this color. 1 liter of an ideal gas. 1 liter of an ideal gas is at a pressure of 2 atmosphere and temperature 300 Kelvin. It expands at constant pressure until its volume is 2 liters. After which it is cooled. After which it is cooled at constant volume until its pressure is 1 atmosphere. It is then compressed. It is then compressed at constant pressure until its volume is again 1 liter. Again 1 liter. It is then heated. It is then heated at constant volume until it is back in its original state. Find the total work. Find the total work done by the gas for this cycle and the total heat added and the total heat added. Let's check the question. 1 liter of an ideal gas is at a pressure of 2 atmosphere and temperature 300 Kelvin. It expands at constant pressure until its volume is 2 liter. After which it is cooled at constant volume at constant volume until its pressure is 1 atmosphere. It is then compressed at constant pressure until its volume is again 1 liter. It is then heated at constant volume until it is back in its original state. Find the total work done by the gas for this cycle and the total heat added. Right? This is your homework. That's all for today. Thank you. God bless you. Assalamu alaikum.